Hello everyone. In this video I'm going to discuss a realistic double slit problem. And you will see that this problem is easily generalized to realistic end slits as well. And so what do I mean by realistic double slits? Well, so far whenever we consider double slits, we've been considering a double slit problem with two small circular apertures, or sometimes we consider these long slits with separation d here, separation small d here. And for this single slit, of course, it has a finite size here, but we assume that this finite size is actually d, capital D here, is much less than the wavelength of light. By a realistic double slit problem, what I mean is that we now remove that restriction. So capital D can be anything. It can be number smaller than the wavelength or greater than the wavelength of light that is used. So let's attack this problem. As in other videos, what we're going to do is we're going to define the axis so that the y-axis is the vertical axis and z-axis is perpendicular to the slit plate and also the screen, and the z-axis connects the slit plate and the screen of detecting the light, and we will consider the diffraction in the yz plane. So now what the task that we have is calculating the light amplitude coming from this slit and that slit. So we need to add those two light amplitudes. You can do this calculation yourself, and the outline is provided. The framework is the same as the one that we use for the grating and the single slit. And the calculation is really not that complicated. It's basically taking into account of the light amplitude coming from this one slit and this from this other slit. So what you will find is that the light amplitude can be expressed as as a product of two complex amplitudes, one summarizing the single slit effect and the other summarizing the double slit effect. So the calculation is actually very pleasant when you factorize. When you see that the complex amplitude is a multiplication of two factors. So then what you find is that the end result in terms of the intensity is this: I equals I0 times the single slit pattern sine square beta over 2 and beta over 2 square times cosine square delta over 2. So I didn't actually derive this, but I just said in words why you get this, and I actually invite you to do that calculation yourself. It's not too complicated calculation if you can handle complex numbers. Okay, so what is the value of what is this symbol beta? Beta is, as we have been defining so far, beta is k, capital D sine theta. What is the delta value here? Delta is k d sine theta. So again, delta is the phase shift of the two lights coming from this upper slit and the lower slit, and beta is the phase shift of light coming from the upper edge of the slit single slit and the lower edge of the single slit. So now you can see that this interference pattern is kind of interesting. So let's plot this interference pattern. Again, what I'm going to do is I'm going to plot this function I as a function of as a function of theta, but I'm going to plot it for positive theta only, because negative theta is a mirror image. So here is 1. When theta is 0, both beta and delta go to 1, and so go to 0, and then these quantities, they all go to 1. So I equals I0 at theta equals 0. Let me first sketch this single slit diffraction profile, which looks like, I'm a little bit exaggerating these intensities in the second maxima and third maxima, just for clarity here. But as a matter of fact, this is actually much lower, much weaker. And now the double slit pattern kicks in. The double slit pattern is actually so notice that double slit pattern is actually given by this function which depends on delta. So it's periodic in delta. But if you look at delta and beta, which one is greater for the same theta? When you have this double slit, capital D is necessarily smaller than this small d. Why? Because if capital D is greater than D, then these two slits will merge. So because capital D is smaller than D, what that means is actually delta is greater than beta, right? So what that means is that consider the second maximum of this cosine square delta over 2. When does it occur? That occurs when delta equals 2 pi. But delta equals 2 pi occurs at a smaller theta than when beta becomes 2 pi. So that means before this minimum, which corresponds to beta equals 2 pi. So let me just this is beta equals 2 pi, and this is beta equals 4 pi. Before beta equals 2 pi occurs, we have for some smaller theta, delta equals 2 pi occurs. So that means, let's say beta equals 2 pi occurs here. Delta equals 2 pi, that's what I mean. Delta equals 2 pi occurs much earlier because delta is greater than beta for the same theta. So in terms of the double slit diffraction pattern, this is maximum, and delta equals 2 pi gives a maximum, but then we have a product of these two functions here. So what happens is that this single slit diffraction pattern acts as an envelope function here, and within that envelope function you have a double slit diffraction pattern which goes on with a shorter period, and it modulates the intensity up and down, and so that's the total diffraction pattern. This solid line is this function I divided by I0. So this rapid oscillation is caused by double slit diffraction, and this low envelope, which is given by that function enclosed by dashed line, It's given by the single slit diffraction. So that's how a double slit diffraction pattern looks like in reality. And this can be generalized to a realistic n slits. All you need to do is you just replace this cosine squared delta over 2 with a function that's appropriate for the n slit diffraction pattern.